Hello everyone, my name is Alex Thomason. For today's presentation on engineering disasters, we are diving deep into a platform I know intimately, the Bell Boeing V-22 Osprey. I spent 20 years in the United States Marine Corps as an aviation hydraulic and structures mechanic, working directly on this aircraft, as well as the CH-46C Knight. Today, we aren't looking at operational history or the human element. We are focusing strictly on the hard engineering, material science, and systems integration failures that have plagued the Osprey, specifically focusing on recent structural and mechanical breakdowns in the Proprotor gearbox, also known as the PRGB. Over the next 9 minutes, we will break down the exact metallurgical flaws behind recent Class A mishaps, the systemic failure to mitigate long-term technical risks, the engineering remedies being implemented right now, and how this is forcing a massive strategic shift in military aviation maintenance engineering. To understand the engineering failure, we must first understand the complexity of the V-22's powertrain. The Osprey is a tilt-rotor aircraft that utilizes two massive rotating engine nacelles at each wingtip. Inside each nacelle is a Rolls-Royce AE1107C, also designated as a T406 turboshaft engine. Both are attached to a Proprotor gearbox. The Proprotor gearbox is a masterpiece of mechanical engineering. Also, and a single point of failure in this instance. It reduces high-speed engine output to drive the 38-foot rotors. Crucially, the left and right gearboxes are linked by a mid-wing gearbox and interconnecting drive shaft system running through the entire wing. If one engine fails, by design, the opposite engine can drive both rotors via the shaft. However, this means the gearboxes are subjected to immense torsional stresses, high vibration frequencies, and extreme thermodynamics as the nacelles rotate through a 90-degree arc during flight transitions. Let's look at the catastrophic material flaw exposed by investigations in recent Class A mishaps, including the tragic 2023 crash off the coast of Japan. The root cause was traced directly back to a material engineering failure inside the high-speed pinion gears of the Proprotor gearbox. This infographic outlines the precise mechanical chain of events and timeline leading to the November 2023 crash, illustrating a devastating intersection of material failure, system overload, and delayed decision-making. Mechanical failure of the pinion gear and Proprotor gearbox. The role of the gearbox. The graphic shows how the Proprotor gearbox connects the engine to the mast that spins a propeller-rotor hybrid. This critical assembly also links both engines across the wings to maintain balance if one engine fails. The flaw. A specific pinion gear within the system contains inclusions, manufacturing weak spots in the metal. Under operational stress, the gear cracked and began disintegrating, spewing destructive metal fragments directly into the transmission. Manufacturing and smelting process of the steel alloys, microscopic impurities known as manufacturing inclusions that were introduced into the component steel. In mechanical engineering, an inclusion acts as a severe stress concentrator. Under the intense cyclic loading experienced during vertical takeoff and flight transitions, these subsurface impurities initiated microscopic fatigue cracks. Over time, due to the high-speed rotational forces, these cracks underwent rapid propagation. The steel essentially experienced a structural degradation from the inside out, reducing its yield strength until the tooth of the pinion gear sheared off entirely, leading to an instantaneous mechanical breakup of the drivetrain mid-flight. This material flaw didn't happen in a vacuum. A recent Government Accountability Office report highlighted a critical breakdown in risk management engineering. Investigators discovered that 34 known system-related engineering risks had remained unaddressed by the program for years. In fact, the median age of 28 unresolved serious or medium technical risks were nearly 9 years. When components like the input quill, clutch assemblies, and pinion gears show earlier signs of accelerated wear, engineers must recalculate the mean time between failures, or the MTB. The systematic mistake here was a failure to dynamically update maintenance engineering parameters based on the real-world data, allowing aircraft components to remain in service past their actual structural lifespan. Despite a 36% to 88% spike in serious incidents over an 8-year average. To fix the catastrophic material failures, the Marine Corps and defense engineers are executing 5 major safety updates outlined in the 2026 Marine Aviation Plan. First, they're physically replacing older vulnerable gearbox components with redesigned parts forged from significantly harder steel alloy with enhanced fatigue resistance. This involves strict metallurgical quality control, utilizing vacuum arc remelting processes to eliminate subsurface inclusions entirely. Second, engineers are modifying the physical nacelle assemblies to change the vibration frequencies transmitted to the gearbox, effectively dampening the resonant harmonic frequencies that accelerate crack propagation. Furthermore, the component inspection protocols have changed. Parts are now subject to advanced non-destructive testing, such as ultrasonic and eddy current testing, to catch microscopic internal flaws long before they reach the flight line. Beyond changing the metal itself, the remedy includes upgrading the digital architecture of the aircraft. The fleet is introducing modernized cockpit computers, high-definition displays, and entirely updating predictive sensor suites. These sensors measure real-time thermal output, chip detection within the oil lubrication system, and micro vibrations inside the proper gearbox. By utilizing real-time digital signal processing, the aircraft's computer can identify anomalies in the gearbox's mechanical signature, such as a unique frequency wave generated by a micro-fractured gear tooth, and alert pilots to execute an emergency landing before a catastrophic mechanical failure occurs. We are effectively shifting from reactive maintenance to sensor-driven predictive engineering. The fallout from the V-22 Proprotor gearbox failures has fundamentally changed the field of aerospace and military maintenance engineering. Historically, different military branches maintained siloed engineering data. The GAO's investigation revealed that the critical hazard reporting, emergency updates, and the mechanical wear data were not being shared consistently between the Marine Corps, Navy, and the Air Force Osprey units. Because of this disaster, the field has evolved to mandate unified, cross-service engineering database. Any anomaly identified by an Air Force mechanic in Japan is now instantaneously ingested in a shared predictive maintenance model that updates lifecycle expectations across the fleet. Even, for example, say the Marine Corps unit that's located in Virginia can access the data that is seen by the Air Force mechanics in Japan. Additionally, the field tilt rotor engineering has completely shifted its baseline requirements. Future tilt rotor platforms like the Bell V-280 Valor are now being designed from day one with fixed engine configurations and modular gearboxes, integrating such health monitoring systems directly into the primary airframe design architecture to prevent the specific mechanical stresses we witness on the MV-22, as well as the CV-22 and all the other V-22s that are across all services. In conclusion, the V-22 Osprey represents a pinnacle of mechanical ambition, but its history serves as a stark reminder that advanced engineering is only as strong as its weakest link, such as metallurgical inclusions in the pinion gears and subpar risk mitigation data systems that sometimes get ignored. But upgrading material steel purity and the integrating real-time predictive sensors, engineering teams are working to ensure the platform can operate safely for far into the future. Collaborated with the AI assistant Gemini. Gemini assisted me with refining the script structure to ensure I met the rigorous 8 to 10 minute academic criteria. Here are some of the references that I used for data, as well as some of the articles that talk about the V-22 in depth. There are also videos within my slideshow that you're welcome to view afterwards. Thank you for your time and welcome any technical questions in the discussion thread. As previously stated in the slide before, if you have any questions or comments about the V-22 military service or general questions, please leave them in the discussion thread for answering.